Good.
Ready when you are.
Okay, my name is Margaret Lockwood, and I'm doing the LSM9DS0 chip calibration project. And this involved learning processing, Arduino, and C++. The chip is for the HiCal Antarctic balloon experiment. And this project is to learn about cosmic rays and neutrino. We've had some other Friday speakers kind of talk about this, but Anita is the main balloon and KU has a smaller balloon called HiCal. And the HiCal trails Anita, the bigger balloon, and it sends kilovolt scale signals directly to Anita and then through the reflection in the ice to study surface roughness. And we've had some speakers, Ivan, Stephen, kind of talking about surface roughness. So this is HiCal, and that's Anita, and this is the payload, and the chip I'm calibrating will be in the payload of HiCal. And so HiCal rotates about like once every second, and so it's important to know the direction and orientation of the payload to send out the signals. So what I'm doing is my chip gives the direction and orientation. And so we have this chip, but it needs to be calibrated, and it's factory calibrated, but that's not really to the standards that we actually need. So I'm calibrating it to give direction and orientation of HiCal in relation to Anita. And so I'll measure the drift in the sensors and make it the sensors so they're accurate and precise. So a little about the chip. The chip's like catchphrase is 9 degrees of freedom, which basically means it has an accelerometer, gyroscope, and magnetometer. And each of these have 3 axes, so that's how they get 9 degrees of freedom. And the accelerometer measures gravity, and that's the accelerometer. The gyroscope measures angular velocity, and the magnetometer measures magnetic fields and magnetization. And this is the magnetometer, and this would be like west and east, and this is north, south, and then the z-axis is up and down. And with these 3 sensors, you can get the yaw, pitch, and roll, and it's yaw, pitch, roll, and heading just gives orientation of the chip. So a little about the setup. When I came in, I didn't really know a lot about breadboards. I've done some like circuit stuff in my physics class, but it was kind of difficult even though I was just copying this. At one point I thought I fried the chip, but it was actually just something on the computer was selected differently. So I learned how to solder for this project. You can see I did a little chip to the pins. So it was fun, but this is the setup. I just copied it from my tutorial online. So since I just was introduced to these like 3 scopes, the 3 sensors, it was kind of hard to understand the data that I was outputting because there was just a stream of numbers. So we decided to make a visualization just to make sure the chip was working at all. So we decided to connect Arduino with this thing called processing, which you can make graphics with. And so we tried to make a 3D graphic, but something ended up being wrong with the computer in the 3D graphics in the Java environment. And the code would work and the visualization would appear the very first time you restarted the computer, but you couldn't re-upload it, so it may have been a memory problem. This kind of took a while to get used to because I didn't know Java, which is for processing. So it took a while, and Stephen helped me a bit with this. So eventually Stephen helped me make this 2D graphic, and it worked, but it was kind of arbitrary, and it kind of, eventually we just needed to work back at the calibration rather than the graphics. But I'll show you some of the visuals. This is a video, can you find it? HiCal. So this was a video of how the 3D graphic looked when it did work. I took this like right after I restarted the computer. But most of the time, we got something different. It didn't actually look like a bunny. Maybe if you like exit out of slideshow mode and try to play it.
Still says
Codec unavailable.
It's okay. You guys can imagine it just moves with the chip. So this is how it usually looked. So it didn't work. So we started to make the 2D graphic, and for yaw we changed the width of an ellipse, we pitched the height, and for roll we rotated the ellipse. And this helped me become a lot more familiar with processing and understanding what yaw, pitch, and roll were, and just understanding the numbers. So even though I kind of distracted from the calibration, I learned a lot, and it ended up helping. So for the calibration, as I said before, it's factory calibrated, but it still needs to be more precise. And when I came into the project, we had some ideas. I worked with Jessica a lot about how to calibrate it, but it was kind of a mystery of how we were going to actually execute it. So first we started with code from GitHub, and it just subtracted the biases. And we ended up only keeping this for the gyroscope, but the GitHub code would have been okay for most projects, but for our project, we needed more precision. So these are some graphs of just using the GitHub. This is the magnetometer moving, stationary, gyroscope moving, stationary, accelerometer moving, stationary. So as you can see, the chip obviously is working, but there needs to be more calibration. So how we decided to start calibrating the accelerometer and magnetometer was figuring out the min and max of the data. And then, so we made a code and we added it to the bias sketch, but we made it so it didn't actually subtract the biases. And it would output the min and maxes. I'm going to show you a little sample of this code on the next slide. So this worked, and it gave us numbers, and it kind of pointed us in the right direction. But there were some issues with the accelerometer. If you moved it too fast, then it would pick up acceleration from you moving it, not just gravity. And for the magnetometer, the computer and like my phone or anything in the room could interfere with the magnetism, so that kind of messed it up. But we ended up just trying to work through that by moving as far away from the computer as we could. So this is the min and max code. So basically, it's reading the data, and then if the minimum that that's set is, if the data being read in is less than the actual minimum, then it will make the number being read in the min. So it just did that, and we had that for this and the magnetometer. So for the accelerometer, how we ended up dealing with moving it too fast, we, at each of the min and maxes for the 3 axes, we would just move it slightly at the max and then slightly at the min, and we would make a histogram of all of these separately. And then it was pretty obvious to find the peak of what should actually be the max or what should actually be the min. So then we used those numbers. And this worked really well, and the numbers that we ended up getting once we added the scale, we mapped it so it was the min and maxes. We would get, this is in meters per second, so 9.8 lying flat and then close to 0, and then up completely upside down, negative 9.8 almost, and then 0, 0. And these are all the different ones. So you can see it working on for the AX, AY, and AZ axis. So we calibrated the magnetometer pretty similarly to the accelerometer, but we had to deal with the magnetism in the room, and we couldn't just use gravity. We had to use a compass to find magnetic north, so that it was more complicated that way. But we ended up aligning it with north, and then we did basically the same thing as making histograms and moving it slightly to find those numbers. And this worked pretty well, except it's a little rough because of the magnetism in the room, but it's a lot closer than what it used to be. So for the gyroscope calibration, the gyroscope is measuring angular velocity. We got a turntable and we put the hardware on the turntable, and first we would rotate it, and I would, with a stopwatch, figure out about how fast it was going, the turntable, in degrees per second, and then I would compare that with what the Arduino chip was outputting the data as the speed. And for all of the axes, and I used 3 different speeds because you could adjust the speed of the turntable. It was about, you only had to multiply by about 1.2 on all of them, and then you would get the number that you should be getting. So this was a pretty easy calibration once we got a hold of the turntable. So overall, the accelerometer and the gyroscope were very well calibrated, and the magnetometer just needs a little bit more work. I learned a lot about computers and how they communicate with Arduinos, and we talked about like binary, and I learned about libraries. I had to download a lot of libraries, and I hadn't dealt with that before. And I learned how to debug and problem solve just through the situation. And it's been really fun, and I learned a lot, so yay.
Just for questions.
Questions? Yeah, Dave.
So Margaret, so I think you obviously did a lot of work in the last week.
Yeah.
I kind of missed the punchline. So if you assume that the HiCal that this antenna is spinning, say once per second, do you have a sense of how well we can measure the azimuthal orientation? How well you can measure, I guess, its heading?
Yeah, so at the end we were about to look at the heading, but we kind of ran out. I looked at it a little bit today, and the heading seemed more calibrated than it was with these, because the heading is coming from the sensors, the numbers. So since this is more calibrated, the heading was more calibrated.
So I mean, I think practically speaking, we can get within, we'd like to get like within 5 degrees or so. Does that seem plausible?
Yeah.
Okay. And then the other thing is that, and again, maybe Jess or Steve know more about this, but is the magnetometer reading coupled to the heading measurement? Are those two tied into each other?
Yeah. So the code that Margaret's using right now takes readings from all 3 of the sensors and determines what the quaternion is, and then uses that to figure out the heading. So they're all the measurements are involved with it.
So how do you, to use it to do a magnetometer correction, does the payload have some lookup table that tells what the local magnetic offset is?
Well, that's one of the things that me and Margaret were talking about. Since the way that the code's usually used, people are at relatively a single like lat and longitude. But since the balloon's going to be moving so much, we'll have to figure out how to get that to. We'll probably have to use GPS and then a lookup table to update it during the flight.
So then we have to tap into the GPS stream coming from.
Right.
Okay.
Yeah.
Good?
Mm-hmm.
Any other questions?
Would you like to go to Antarctica?
Yeah, that would be awesome.
Okay, I'm just curious.
Maybe next summer.